Today I'm going to start talking about numeric integration, and really what we're going to be doing is talking about trapezoidal rule and Simpson rule. So I'm going to jump right into it. We use trapezoidal rule and Simpson's rule when we need to evaluate a definite integral whose antiderivative or integral can't be found using the fundamental theorem of calculus. So when it is difficult or we don't know how to figure out the integral, we have no other choice but to use an approximation. But a trapezoidal rule is going to give us a much better approximation of the area underneath the curve rather than just using regular rectangles for lower or upper sums. So trapezoidal rule really just creates these trapezoids that are here. And so we're going to start looking at the actual formula for trapezoidal rule. But you don't have to memorize the trapezoidal rule if you can just remember really all we're doing is finding the area of each of these trapezoids. However, I will use the formula when solving a problem just so you can see how the formula could be used. What I want to talk about is I'm actually going to go ahead and put another trapezoid in here for later. There's a reason for this. So I'll lightly draw that in. And that would be x1 and this would be x2 for that part. We'll get into that. But the area of the first trapezoid is found by taking, if you remember the formula for a trapezoid is 1/2 base, it's 1/2 the height times the bases added together. What I really have written here is I have the bases added together divided by 2 times the height. So I have base plus base here divided by 2 times the height. That is still the exact same thing as that formula, okay, because you can rearrange things. Well, base plus base, this is your bases. Those are the two sides that are parallel to each other. That would be the height of the function. That would be this side. And the base here would be the height of the function of x sub 1. So those two things are being added together. We're dividing them by 2 because that's what the formula calls for. And then the height of the trapezoid is this side right here. This is the height. And the way we're determining the height is by taking the b minus a divided by n. Where are those things coming from? Well, this is my b and this is my a. And then this is the number of trapezoids there are here. So this is the number of trapezoids. Well, in this particular problem, I only had one trapezoid drawn. Now I have 2. But what you're doing is you're taking whatever your lowest number is, so the lowest number on your integral, your lower bound, and your upper bound, you're subtracting those two. So this is your upper bound, and this is your lower bound. Okay, this whole thing represents the height, though. Okay, so let's look at the formula, and you can see, holy cow, this is a lot of information. There's a lot going on in this formula. I don't think I can memorize this. Well, that's fine. That's why I said you don't have to. You just have to understand that really what you're doing is creating a bunch of trapezoids underneath there. But it will be easier to compute the formula or to compute the answers if you do memorize it. So you got to kind of think about what you want to do. It's totally up to you. Again, I'm going to be using the formula so you can see how it works. But I want to show you where this formula comes from and why are there 2's in front of these. That goes back to this other thing where I just got through talking about having this other trapezoid. Can you guys see that on this trapezoid right here, okay, the black line would come down here. So there's actually 2 of these x sub 1's, which would be your f of x sub 1. So you'd be using that as your base twice. So that's why there's a 2 in front of there. So you use the first part 1 time and the last part 1 time. That's why these do not have a 2 in front of them. This 2 on the bottom comes from the 1/2. That's all these things were being divided by. We just brought that out front. And then the b minus a was your upper bound minus your lower bound divided by the number of trapezoids that there are. So in the next video, I'll actually go ahead and use this formula and compute the answer. Alright, so here's my formula, so I'll be glancing back and forth at this for this next problem. What I'm going to do is I'm going to use trapezoidal rule to approximate the value of the definite integral. what I think I'm going to do is actually just write the trapezoidal rule so I don't have to keep flipping back and forth between the two slides. So what it says is that if I'm going to evaluate the integral from a to b of f of x dx, I would take and I would do upper minus lower bound divided by 2n times f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 dot dot dot, and then 2 of f of x sub n minus 1, and then plus f of x sub n. Okay, now that I've got that written up here, I won't have to keep going back and forth. So if I start out by doing this, I'm going to go b minus a, well, that would be 3 minus 2 all over 2 times my n is 4, meaning I've got 4 trapezoids. And then I'll be multiplying that by the function of each of those values. Well, I need to first think about breaking up 2 to 3 into 4 rectangles, or trapezoids. And I don't actually need to create those trapezoids. I'm just going to kind of draw it. So this would be creating 2 trapezoids, which would be a 5 halves. This would be creating, now I'd have 3 trapezoids, and this would be 4 trapezoids. So this would be the value of 2 3/4, which is 8 11/4, and then this would be the value of 2 1/4, which would be 9/4. So you can also describe this as 10/4 if we wanted to. So what I'll be then doing is plugging in each of those values. So I have 2 over, my first value here is a 2. So I'll be plugging in 2 into the x. So there's my f of x sub 0, plus I need to put a 2 out in front because I've actually have 2 of these. When I create my trapezoids, I'd have 2 of those sides right here. So I'll be saying 2 divided by, I'll put 9/4 squared here, plus I have 2 of the next ones. So it'd be 2 over 5 halves squared. And all I'm doing is taking these values and plugging them in over here for x, okay? Plus 2 times 2 over, this would be 11/4 squared. And then plus, I'm going to plug in the 3, so it'd be 2 all over 3 squared. And then I just need to compute this. Now, I'm going to tell you in the video, you guys should try to compute this on your own. You do get this to approximately be equal to 0.3352. Work with your calculators and see if you can get that to work out. The next thing we're going to start to talk about is Simpson's rule. Now, I'm not going to derive this as I did with the trapezoidal rule. It would take way too long for these videos. It is described to you on page 314, and it is a little bit more complicated to understand. What I want to point out to you is there's a couple differences. The trapezoidal rule has b minus a divided by 2n, and the Simpson's rule has b minus a all over 3n. And then if you also look, all the coefficients on the other one was 1, 2, 2, 2, 2, 2. In the Simpson's rule, it's 1, 4, 2, 4, 2, 4, 1. What that means is that I definitely would have to have n to be an even integer. So whenever they're asking me to do Simpson's rule, they'll ask me to pick an even number of of areas underneath the curves of sections that I'll be breaking that up into. I don't have time to finish the Simpson's rule on this particular page, but I will do that on the next video. Okay, so what I'm going to do is I'm actually going to compute this same problem I just did with a trapezoidal rule with Simpson's rule, and you're really going to see very, very little difference in the answers. Simpson's rule just gives a little bit better approximation than the trapezoidal rule, but it's still, so that makes trapezoidal rule basically just about as good. Simpson's rule, I meant to write down the formula before I started this video and I forgot, so I'll go ahead and do that really quick. It says that if I'm evaluating an integral from a to b of f of x dx, it equals b minus a all over 3n. And then you'd have f of x sub 0 plus 4 of f of x sub 1 plus 2 of f of x sub 2 plus 4 of f of x sub 3 4 of the x sub minus 1, and then plus the last part, and I ran out of space, but we get the idea here. So we're going to start out by taking the b minus a part, so it would be my upper bound minus my lower bound, all over 3 times the number of times I'm breaking this up into, which is 4. And then we'll just start plugging in the values. So again, I'm going to be using those same values as I did on the last problem. I'll be using the 5/2. I'll be using the 11/4, and I'll be using the 9/4. Those are broken up into equal subsections. So I'm going to take and I'm going to write 2 over 2 squared plus 4 times, plugging in now 9/4, so I'd have 9/4 squared plus, now my coefficient's 2, and I'll put 2 over 5/2 squared plus, now my coefficient's 4, remember, alternates back and forth between 4, 2, 4. First and the last are always coefficients of 1, so I have 11/4 squared. And then plus, remember the last one has a coefficient of 1, so it'd be 2 over 3 squared. Now when you compute that again, I'm not going to spend time putting this in the calculator and showing you guys how to put this in the calculator. When your calculator reads this, you will get 0.3334. You can see that the other answer was 0.3352. Very, very, very close to each other, so both good approximations.